I want to recap the lesson from the last 2 days where we discussed the compositions of compounds, how we can express that information. And there's two common ways to do that. One is by using the formula, which tells us the number of atoms there are in the compound, as well as by percent composition, by mass. And these two concepts are related. So in day one, we took a look at the formulas, and we considered these three molecules: formaldehyde, which is CH2O, and acetic acid, C2H4O2, and glucose, C6H12O6. These all appear similar in some ways, but they're very different substances from each other. In fact, this formaldehyde is toxic, is a toxic substance, whereas glucose is necessary, is the key ingredient to cellular respiration, which is what's keeping you alive right now. Because these are different molecules, they have different sets of properties. Now, we also introduced a new term, which is empirical formula. Now, the empirical formula is the lowest whole number ratio of the molecular formulas. So in these three examples, they all have the same empirical formula. And at this point in the lesson, you may have been wondering why even have this concept of empirical formula at all? Because I told you in earlier lessons that it's not proper to reduce molecular formulas because they're different from each other. So we'll get into why this is a thing in a minute, but it is the lowest whole number ratio of your molecular formulas. At this point, we shifted gears and we took a look at percent composition by mass. So let's create a new section here. And this is percent comp by mass. So the way we determine the percent composition of a compound, this is, again, another way we can describe or express the composition of compounds, is to get the mass of each element in that compound and put it over the mass of the compound which that element is in. Multiply by 100 to turn that into a percent. That's the formula we use to get percent composition by mass. And so this is just a format that is very intuitive for many students. But the example that I posed to you was using ethanol. And I said, what if we had 12.3 grams of ethanol, which is C2H6O, which I just wrote it this way to show that it's an alcohol. And I said, well, what if I had 12.3 grams of this alcohol, and I want to know what is the mass of the carbon component in this compound? And we had a little trouble coming up with an approach to this problem. I pointed out that percent composition is an intensive property of matter. So what that means is it doesn't depend on the quantity of this substance. It's the same. So whether you have 12.3 grams of ethanol, whether you had 12 million grams of ethanol or 0.001 gram of ethanol, the percent composition is going to be the same. Therefore, to make this problem as simple as can be, we want to use 1 mole of the compound. And that's going to make calculations much easier. Let me show you what this looks like. So if we consider having 1 mole of ethanol, that means the carbon component is going to have 2 moles because of the formula, we know this. So 2 moles of carbon. And we also therefore know that if we have 1 mole of ethanol, then we have 6 moles of hydrogen. All right, don't forget that hydrogen on the hydroxyl group. And we also know that there is 1 mole of oxygen in every mole of ethanol. Again, we're doing this because percent composition is an intensive property. Didn't matter, and we'll later apply to this 12.3 grams. All right, right now we have all our information in terms of moles, and what we want is grams. All right, again, we want grams because the formula for percent composition requires mass, and right now we have moles. So in order to go from moles to mass, or mass to moles, which you will do very often from here on out in chemistry, we need the molar mass. That's right on the periodic table. All right, so let's get the molar mass and use that as a conversion factor to get rid of moles and end up with grams so we can get the mass percent. All right, so the molar mass for carbon is in 1 mole of carbon is 12.01 grams of carbon. All right, cancel these units out, and let's do the same thing for the other 2 elements. In 1 mole of hydrogen, there is 1.008 grams of hydrogen. Cancel these units out, and one more time, in 1 mole of oxygen, there's 16.00 grams of oxygen. If you're wondering where I'm getting these numbers from, it's right off the periodic table. That's what the mole does for us. It converts the atomic units into practical units of grams. All right, so let's punch these numbers in our calculator. I've already done this, so you can check on your end. All right, so why did we do this? Always make that bigger connection. We need mass ratios of the elements to the compounds. These are your masses of each individual element in the compound of ethanol. Now what we need to do is get the mass of the compound, ethanol. And since these are the components of it, if we add them up, we'll get the molar mass of the compound. So in 1 mole of ethanol, when you add these up, we get 46 grams, the molar mass, 46 grams per mole. All right, now we're ready to use this formula, mass of the element over mass of the compound times 100 to get the percent composition. All right, we'll put each of these element masses over the mass of the compound, which is what we just added up, multiplied by 100. And for carbon, the mass percent is 52.14%. Right, that's for carbon. For the hydrogen is 13.13%. By mass, ethanol is hydrogen. And 34.73% of ethanol by mass is oxygen. And these all should add up to 100%. That's what we covered in day 1. So day 2, to recap what we did the previous day, the big picture, again, was expressing the composition of compounds. All right, so how did we just do that? We took a formula. In the previous example, it was ethanol, and we were able to turn that into percent composition by mass. And just give you some rounded figures, ethanol is about 52% carbon, 13% hydrogen, and about 35% mass, by mass, oxygen. So it would be reasonable to say, if there's a way to use the formula of a compound, that's one way to express composition, using the formula, to get the percent by mass of that compound, of its constituent elements, by mass. So it should be reasonable to think that given the percent by mass of a compound, we should be able to deduce a formula. All right, and so this part is often less intuitive or less obvious for students. So in order to present this in some context, I use an example of a combustion device. Because a lot of times, students, when they're learning empirical formulas, are just memorizing steps, like 1 through 5, or however many steps the teacher describes it in, and they don't know why they're doing what they're doing. They're just memorizing stuff, and that's no fun. When you're learning, you want to always try to make connections, especially to a real-world scenario. So this is one of them. We have a combustion device. In this combustion device, we have several chambers, and in one end, we're going to feed it, we're going to input oxygen in excess. Let's say a building burned down in our town, and we found this mysterious substance, detectives found, and they hand it over to you because you're the expert chemist, and you determine that it's this unknown compound is only made up of carbon, hydrogen, and nitrogen. And the detective's like, we need to know what the substance is, get on it. And so you put it into this combustion device, and we heat up this furnace component, and that's going to produce carbon dioxide. I'm going to highlight the element that we're interested in purple. And then the hydrogen component of that compound, that mysterious compound, is going to combine with the oxygen and form water vapor. And these substances are going to move along to the next chamber. We have a chemical in here that absorbs the desired element that's passing through this chamber. So let's say in chamber 2, this is some sort of hydrogen absorber. Hydrogen absorbing substance. For example, this can be magnesium perchlorate. And because we know the mass of this magnesium perchlorate, before it started absorbing the hydrogen, by the way, I'm simplifying this. This is not exactly how it works, but I'm just want to emphasize the concept. So before this magnesium perchlorate, we have a mass, and then we can mass it afterwards, and that difference in the mass, we can conclude, was the mass from its absorption of hydrogen. And so I gave you some numbers that'll work out nicely at the end, and that mass turns out to be 0.01875 grams. So anything that is absorbed into this absorber is the hydrogen, and we can say that hydrogen must have come from our mysterious substance which we were trying to identify. So now we have the remaining passing into our third chamber, and here we have a similar mechanism where we have some chemical that's going to absorb the carbon that we're interested in. So let's say a carbon absorbing substance. And something like that, something like sodium hydroxide might do that. Because we can get the mass, so anything that has carbon passing through this chamber is going, this material is going to absorb that carbon. And because we know the mass before and after the absorption, we can calculate the mass of the carbon, which must have come from our mysterious substance we're trying to identify. So the number I gave you was 0.04470. Right? This device measures out to 5 decimals. And then I asked you, all right, and any excess oxygen just comes out the other end. So I asked you, what is the percent composition of our unknown chemical? So you only had to know what we learned the previous day to figure this out, which is the mass of the element, which we give you here, over the mass of the compound, which we did not give you. So I actually did give you that. So that value is 0.1156 grams is the mass of the sample in question, right? So I gave you that at the start of this example. All right, multiply that by 100, and the same thing here, multiply that by 100. So we calculated that the mass percent of the carbon in this unknown substance was 38.67% carbon. And we calculated the hydrogen. If you do this computation, multiply that by 100, the mass percent for the hydrogen component is 16.22% hydrogen. All right, because the only other substance left is the nitrogen, the percent nitrogen was 45.11% nitrogen. It's the only other substance, and all three of them need to add up to 100%. So let's just step back and understand before we move into the final, into the next stage here, is understand what is going on here, right? Detective found a mysterious substance, a house burned down or a building burned down, and you're tasked to figure out what that substance is so we can either use it in court, forensics court, as evidence against possible suspect. So the question is, how can we take the percent composition and get a formula? All right, so let me take you back. That was our goal here. All right, how do we do this? All right, well, you want to follow these steps, and I'll give you the reasoning behind each of them. So when you're given percent composition, and you will certainly see this on your test, we give you percent composition, we're going to ask you to determine the formula, empirical and molecular. So let me show you how to do that. The first thing you want to do is turn these percentages into grams, right? And instead of using the original sample, the mass of the original sample I gave you, because you're going to end up making it much harder than it needs to. Remember, these are intensive properties, so we don't need to use the actual sample mass. We'll get the same results no matter what mass of sample that we use. Therefore, we want to use the easiest numbers. And when you're dealing with percentages, the easiest number to work with is 100. So if we say, imagine we have a 100-gram sample, then that means 45 grams of it was nitrogen, and 16 grams of it is hydrogen, and we can say 38 grams of it is carbon. And we want grams because we need moles eventually to get a formula, right? So here's the ultimate goal. Put this right here, underneath here. We're trying to get the detective. The detective wants to know what this substance is. We're trying to get an answer in terms of C something, H something, and N something. We want to know what the formula is, right? And to get these X, Y, and Z subscripts, we need to get moles, information in terms of moles. Right now we have percentages. So that's why we're going to consider having 100 grams. All right, let's just see what this looks like. Step one, we are going to change the percentages to grams, right? This will, if nothing else made sense, hopefully it did, but memorizing these steps, and unfortunately this is what happens with most students, they just memorize the steps and don't know why they're doing it. But these are the steps that will get you the answers on your test. Percent to grams. If we have, so I'm going to start with carbon on the right side of the screen. If we had a 100-gram sample, the carbon component would make up 38.67 grams. Similarly, if we had a 100-gram sample, the hydrogen component would make up 16.22 grams. And the nitrogen component would make up 45.11 grams. All right, you can see why I didn't even need a calculator to do that, because I assumed we had a 100-gram sample. All right, so the next step I'll do here in a different color, you want to change that grams to moles, because that's one way to interpret a formula. The X, the Y, the Z are all mole ratios of each other, between each other. All right, so we need to turn grams into moles. All right, so by now, hopefully you're experts at doing this. Anytime you go between mass and moles, you need the molar mass, which is on the periodic table. Let me just label the substance here. That's carbon, this is hydrogen, and this is nitrogen. All right, so step 2, we're going to convert the grams to moles using the molar mass. We don't need super precision here, so just maybe 1 decimal should be fine. So 12.0 grams of carbon is 1 mole of carbon. All right. Cancel these out. 1.01 grams of hydrogen is in 1 mole of hydrogen. And 14.0 grams of nitrogen is in 1 mole of nitrogen. If you punch those numbers in, you get 3.2 moles of carbon, 16.0 moles of hydrogen, and 3.2 moles of nitrogen. Now at this point, we have our mole ratios. Let's see what this could look like if we stopped here. That means our formula would look like, let's keep this in that same blue actually, C 3.2, H 16, N 3.2. And you might say, well, there's a formula, right? So there's, I got that from there, I got that from there, and so on. But you know, this is not how you write chemical formulas. You can't have decimals in the subscript of the formula. So now our next step is going to address that. We need to get rid of these decimals. So next step I'll do in green. Next step is you want to take the smallest mole and see how many times that goes into each of the other moles. So the smallest mole is 3.2. So we're going to see how many times 3.2 goes into each of the other results. The reason we're doing this is this guarantees at least one of your numbers is going to be a whole number, an integer. The one you're dividing it into itself is going to be 1. So these are 1s. We've gotten rid of 2 decimals. Hopefully, the best case scenario, they'll all turn out to be whole numbers. And that's what's happening here. All right, now this number it's 4.9 something. So that's, if it's really close to a whole number, it's a whole number. So these will give you the empirical formula. So the empirical formula is your first major answer. The empirical formula is C1, and we don't write ones, H5, that just came, these are just coming from here, and N1, but we don't write ones. So here's our empirical formula. Now, let me go back and reemphasize something. If this number was like 4.5, you don't round that up. So you'll have to multiply all the numbers through by 2 to get whole numbers. If this number was instead like 4 1/3, then you'll have to multiply all your sets of numbers by 3. So you'll turn, you have to multiply everything through in order to get whole numbers, because that's the point of this step, to get rid of the decimals. All right, now, in our class, you're not likely to see anything other than halves or thirds or 2/3. Right? Now, you might see a quarter or even a fifth, but that's highly unlikely. It's not a typical stuff something we would ask you on a test. All right, so the most common thing is they just turn out to be whole numbers like here. That would be awesome for you. It might be a half, then you multiply through by 2, or it might be a third and multiply by 3 and so on. All right, and if you're not good with that, you can just multiply by 100. You'll just have to reduce, it'll take you much longer. The point is you need to get an empirical formula, the lowest whole number ratio. All right, now the final step, because the whole point of this was the detective does not want this. That could be any number of things. Well, actually, in this case, there's only one molecule with this empirical formula. But in other problems, there could be more than one molecule that have the same empirical formula. So we want to get the molecular formula. That's our ultimate goal. What is in that substance? In order to get the molecular formula, you have to know 2 things. All right, one we have to give you, and that's the molar mass. And you want to see how many times the empirical formula mass goes into it. All right, so let's say we give you the molar mass of 31. Let's say, example. Let's say the molar mass of this substance in our furnace device, 31 grams per mole. So how many times does the empirical formula mass go into that? Well, let's do that. The empirical formula is here. So carbon, all right, let's just do it up here. I'm not stretching this out. All right, so carbon's mass is 12 plus 5 from the 5 hydrogens, and nitrogen is 14. That's the empirical formula mass is also 31. So in this example, the empirical formula mass, because it's the same as the molar mass, is the same as a molecular formula. So the molecular formula is the same as its empirical formula. In this case, it's CH5N. And you tell that to the detective, and the detective figures out, oh, that thing is used to make explosives. This house or building was intentionally blown up or something. All right. Or they might find out, well, this is just carpet. It might have been an accidental fire. Well, this is not carpet, but this one could be. Now, let me give you the other scenario. What if we said instead the molar mass is 93? This doesn't exist, I don't think, but let's say it did. Well, then you can see that the empirical formula mass goes into the molar mass 3 times. Right? That means you need to multiply the empirical formula 3 times to get the molecular formula. So if that was the case, the molecular formula would be C3H15N3, which I just made up. So this is not something that exists, I don't think. All right, so there is everything you need to know about how to express the composition of compounds. We did a lot in this recap video. All right. Formula to percent composition, that's the one students generally have no problem with. Taking percent composition data and getting the formula, You're going to have to memorize some steps, and hopefully you know the reasons behind those steps. Good luck.